Welcome to The Explainer. Today, we're diving into what makes our electronic and digital systems stable. We're going to peel back the layers of signal processing to figure out what separates a clean, reliable signal from, well, total chaos.
Yeah, we've all been there, right? At a concert, and suddenly you get that ear-splitting squeal. That's audio feedback, and it's a perfect real-world example of a system going completely haywire. See, what's happening is a tiny sound gets caught in a loop, getting amplified again and again and again until it's the only thing you can hear.
Okay, so to really understand what's behind that awful squeal, we need to get on the same page. What do we even mean by stable when we're talking about signal processing?
All right, the core idea here is something called bounded input, bounded output stability, or BIBO for short. And honestly, it's a pretty simple promise. It says that if you put a normal, well-behaved signal in, something that doesn't just fly off to infinity, you should get a normal, well-behaved signal out. You know, like a musician's voice goes in, the sound from the speaker comes out. If a system can't keep that promise, if any reasonable input can make the output just explode, well, that system is unstable.
But that's the real challenge, isn't it? How can we tell if a system is going to go haywire before we even turn it on and ruin the show? To do that, we need a way to look under the hood, to really analyze a system's core identity.
And that brings us to something really cool, a system's hidden DNA. It turns out that every single system has this unique kind of fingerprint, a genetic code that tells us exactly how it's going to behave under any condition.
So, how do we read this DNA? We use these incredibly powerful mathematical tools called transforms. You might have heard of them, the Laplace transform for analog stuff and the Z-transform for digital. The best way to think about them is like a pair of magic glasses. Normally, we see the world in the time domain, watching a signal change over a few seconds. But these transforms let us switch our view to the frequency domain. Suddenly, we can see all the different tones, all the individual frequencies that are hidden inside that one signal.
Now, once we're looking through those glasses, in this frequency view, every system reveals its true identity. It's called a transfer function. And don't let the name scare you. At the end of the day, it's really just a big fraction, a ratio of two polynomials, that acts like a complete blueprint for how that system will react to any frequency you throw at it. And this is where we find the actual genes, the DNA of our system. It's all about the roots of those polynomials. The values that make either the top or the bottom of that fraction equal to 0. The roots from the top part, the numerator, are called zeros. Think of these as frequencies the system just wants to crush or silence. The roots from the bottom part, the denominator, are called poles. These are the system's sweet spots, the frequencies it absolutely loves and wants to amplify, where it naturally resonates. So now we have this collection of poles and zeros. What we do next is we actually plot them on a special kind of graph, a complex plane. We mark the poles with an X and the zeros with an O. And what we get is this amazing map called a pole zero plot. It's literally a visual guide to everything that system is and how it will behave. And this map, this is where it all comes together, because this simple plot of X's and O's holds the secret. It gives us a single golden rule to tell, just by looking if our system is stable or if it's a ticking time bomb.
Okay, so for analog systems, this map is called the S-plane. And here's the deal. It's all about the location of the poles, the X's. If a pole is on the left-hand side of the map, it represents energy that fades away over time. That's good. That's stable. But if a pole wanders over to the right-hand side, that represents energy that grows and grows exponentially forever. That's bad. That is textbook unstable.
So that gives us our golden rule right there. For an analog system to be stable, all of its poles, every single one, has to be in the safe zone on the left side of that map. It doesn't matter if you have 100 poles in the safe zone. If just one of them crosses that center line into the right half, game over. The whole system becomes unstable.
So what about the digital world? Well, when we move from analog to digital, the map changes. The rules of the game are the same, but the playing field looks different. That entire infinite safe zone on the left gets mapped into a new, tidy little shape. The area inside a circle with a radius of 1. We call this the unit circle.
And this table just lays it all out perfectly. For analog systems on the S-plane, the safe zone for poles is the entire left half of the plane. For digital systems on the Z-plane, the safe zone is inside the unit circle. It's the exact same principle, just a different map for a different type of system. But going digital isn't just about a new map. There's a catch.
The whole process of taking a smooth, continuous analog wave and chopping it up into a series of digital numbers, well, that act of sampling brings its own set of problems. There are two big pitfalls we have to be super careful about. Yeah, when we take that beautiful, smooth wave and turn it into a bunch of separate digital snapshots, we can accidentally create ghosts in the machine. These are artifacts, illusions that show up in our digital data that look totally real, but they weren't in the original signal at all.
So let's break down the two biggest culprits here, the most common digital ghosts you'll run into: aliasing and spectral leakage.
Okay, first up is aliasing. This is what happens when your sampling rate is just too slow for the signal you're trying to capture. The classic example is trying to film a helicopter spinning blades with a camera that has a slow frame rate. On screen, the blades might look like they're spinning really slowly or even backwards. That's an illusion. In the world of signals, aliasing is when very high frequencies get disguised as brand new, false low frequencies. They create an alias of themselves that shouldn't be there.
Exactly. These are imposter frequencies. They are complete fakes that weren't in the original sound at all. And here's the really bad part. Once aliasing happens, it's game over. You can't undo it. Your signal is now fundamentally and permanently corrupted.
Now, spectral leakage is a whole different beast. This isn't a problem with how you sample the signal, it's a problem with how you look at it. See, we can only ever analyze a signal for a limited amount of time, right? We have to look at a small window. It's kind of like trying to figure out the exact musical note someone is singing by only hearing a tiny, abrupt snippet of it. Because you only have that little piece with a hard start and stop, the energy of that pure note seems to leak out and spread into the frequencies right next to it. So the result is like getting blurry vision. You're not seeing fake frequencies, like with aliasing. Instead, the true frequencies just get smeared out. You lose sharpness and precision, and it becomes really hard to tell the difference between two frequencies that are really close to each other.
So let's put these two side by side just to make sure it sticks. Aliasing? That's a sampling problem. You sample too slow, you get fake frequencies. The only cure is to filter out those high frequencies before you even start sampling. Spectral leakage? That's an analysis problem. You're looking at too short a window of time and the real frequencies get blurry. The fix here is to use a longer observation window or apply some clever shaping to that window.
Okay, so let's wrap this all up. What are the big takeaways? First, system stability is all about one thing, the location of its poles. Where do those X's live on the map? For analog systems, they have to be in the left half plane. For digital, they have to be safe and sound inside the unit circle. And second, when you step into that digital world, you've got to watch out for those two ghosts in the machine: aliasing, the creator of fake frequencies, and spectral leakage, the blurry vision problem.
And that really brings us to the big picture. Our entire modern world is built on these digital systems. From the filters that make your phone calls clear, to the complex controllers in your car's anti-lock brakes, these principles are working silently in the background, all the time, keeping things stable. So now that you know the rules of the game, the dangers of a straight pole or improper sampling, where do you see this stuff at play in your everyday life? You might be surprised how often you spot this hidden layer of engineering that makes our world work.